We walk around every day treating the ground beneath our feet as a permanent fixture. But that solid crust is a temporary illusion. The mountains, the continents, and the ocean floors are merely the thin, cooled skin of a massive thermodynamic engine churning beneath us. To master physical geography, memorizing the surface isn't enough. We have to map the invisible interior forces that dictate every valley and peak. This diagram shows Earth's internal layers, stratified like a machine, working from the core outward. We will trace a direct causal chain from this deep core heat upward to the creation of rocks, and outward to the shifting of continents. And this planetary engine has been running continuously for 4.6 billion years. Every border and coastline on a modern map represents the current, temporary output of an ongoing physics equation. Because seismic waves change speed and direction at every density boundary, we can echolocate the exact transition points of the interior. By matching these wave patterns with the metallic density found in fallen meteorites, we can model the world beneath us with mathematical precision. This graph illustrates the first thermodynamic rule of the interior: temperature increases with depth. Initially, it rises a sharp 1 degree Celsius for every 32 meters, before the curve flattens out as we push deeper. The second rule is that density also increases with depth. This extreme pressure forces the Earth to separate into distinct chemical layers. This table details the outermost layer, the crust. Notice the stark dimensional difference between the less dense continental crust, at roughly 30 kilometers thick, and the highly dense oceanic crust at just 5 kilometers. They possess distinct chemical signatures. The continental crust is defined as Sial, silica and aluminum, forming lighter granite. The oceanic crust is overwhelmingly denser basalt. Moving one layer deeper, we hit the mantle. This region is defined by a heavier chemical composition known as Sima, composed of silica and magnesium. Within the upper mantle lies a critical sublayer, the Asthenosphere, or Derbalta mantle. Here, rock is subjected to such extreme conditions that it becomes partially molten, churning and generating the magma that drives surface geography. At the very center sits the extreme pressure core, composed of nickel and iron, acting as the ultimate heat source for the entire planet. The massive contrast between this boiling, dense core and the cool, brittle crust creates a highly pressurized system. The Earth is constantly desperate to release this internal energy to the surface. When that highly pressurized magma from the asthenosphere finally breaches the crust, it initiates a recycling program that has been running for billions of years. This flowchart outlines the rock cycle, a completely closed-loop system of transformation where surface materials are constantly created, destroyed, and reborn. First are the igneous, or primary rocks. Because they form directly from cooling magma, their structure is crystalline and they are entirely devoid of fossils. Next are sedimentary rocks. These form when surface erosion wears down existing rocks, depositing the debris into strata, layers that eventually trap fossils, coal, and oil reserves. This creates a fascinating geographical paradox. Sedimentary rocks cover 75% of the Earth's surface, yet they make up only 5% of the crust's total volume. Finally, we have metamorphic rocks. These form when either igneous or sedimentary rocks are dragged back down toward the mantle and subjected to immense heat and pressure, altering their structure without fully melting them. Through this intense pressure, a fragile sedimentary rock like shale compresses into hard slate, and common limestone transforms into solid marble. Every rock you see on Earth, regardless of its current state, is a temporary phase of matter dictated by its position in this thermodynamic cycle. Zooming out from individual rocks to a global scale, we have to redefine the crust. Combined with the rigid uppermost layer of the mantle, it forms what we call the lithosphere. But this lithosphere is not a single solid shell. It is fractured into 7 major and roughly 20 minor tectonic plates. The mechanical explanation for how these massive plates move is plate tectonic theory, formalized by scientists like Harry Hess and W. Jason Morgan in the 1960s. The core mechanism relies on radioactive decay within the asthenosphere, which creates massive thermal convection currents. These rolling cells of heat act like subterranean conveyor belts, literally dragging the brittle plates resting above them. Where these convection currents pull two plates in opposite directions, they create a divergent margin. This gap allows magma to rise up, cool, and forge brand new crust. Hess's mechanical proof validated a much older hypothesis proposed by Alfred Wegener in 1912, the theory of continental drift. Looking at this map of the Permian era, we see Wegener's claim. During the Carboniferous period, all landmasses were merged into a single supercontinent named Pangaea, surrounded by one massive ocean called Panthalassa. Over millions of years, those deep thermal convection currents fractured Pangaea, sending the fragmented continents drifting toward their modern coordinates. The physical evidence is embedded in the coastlines. You can see it in the distinct jigsaw fit of South America and Africa. It is also verified by biological proof. Identical glossoparous plant fossils, like these, have been found embedded in rock across vastly different climate zones in India, Madagascar, and Antarctica. There is structural proof. Mountain chains in Brazil share the same pre-Cambrian age and composition as rock structures in Angola, aligning perfectly when the continents are reunited. Plate tectonics is the unifying theory. It proves that the continents are essentially just rocky rafts, floating on a slow-moving sea of churning magma. To truly understand modern geography, we have to overlay this constant tectonic movement onto the geological timescale. The massive economic resources we rely on today are the direct results of specific ancient tectonic accidents. During the Carboniferous period, tectonic shifting caused dense prehistoric forests to sink into massive rifts, burying them under intense pressure over millions of years. This specific burial event created the Gondwana rock formations, which today hold the vast majority of India's primary coal reserves. Moving forward to the Cretaceous period, plate separation triggered violent volcanic activity. In western India, immense lava flows erupted and eventually cooled, forming the thick, tiered basalt structures we now know as the Deccan Traps. The slow surface weathering of these specific Cretaceous igneous rocks created the incredibly fertile black soil that drives modern agriculture in the region today. The Earth's internal thermodynamic engine, the rock cycle, and tectonic drift are the invisible architects of our modern geography, economy, and history.